Hello, welcome back to this next video where we are going to again discuss the factors affecting chemical shift. In the previous videos, we have discussed about the electronegativity and the hybridization effects. I would like to briefly flash the slides before I go for the next topic for today's discussion. So in this particular video, I would like to discuss about the magnetic anisotropy. So in the previous video, while I was discussing the sp2 hydrogens and about the aromatic hydrogens, aldehyde hydrogens which are sp2 hydrogens, and the sp3 hydrogens which are the acetylenic hydrogens, I mentioned there is the difference in the delta values where they appear. The sp2 hydrogens usually appear at the vinylic hydrogens, they usually appear at 4.5 to 7, whereas the aromatic hydrogens, they appear at 7 to 8, and the aldehyde protons, they appear at a further downfield region which is 9 to 10 ppm. So compared to that sp2, sp3 hydrogens, they appear at the very shielded region, that is 2 to 3. This was because of the anisotropy. So in this particular video, I would like to discuss about the magnetic anisotropy and its effects and how it affects the chemical shift values. So coming to the benzene, which has the sp2 hydrogens, the benzene hydrogens are said to be deshielded by diamagnetic anisotropy of the ring. So we know that what is diamagnetic anisotropy? Diamagnetic anisotropy is the induced magnetic field because of the circulation of the electrons, or the localized field, magnetic field which is generated because of the circulating electrons, and this field, or the localized field, is opposing the external magnetic field. This whole process, we know that it is called as diamagnetic anisotropy. So when we take up the aromatic ring, the pi electrons in the aromatic ring are induced to circulate around the ring in response to applied magnetic field. So this is the circulation of pi electrons, and because of the circulation of the pi electrons, there is an local magnetic field which is generated, which is in this particular direction, and this local magnetic field actually opposes the external magnetic field, which is B naught. But however, you can see on the periphery of this ring, the flux lines are in the direction of the applied magnetic field. If you see here, the orientation of this magnetic field is somewhat aligning the external magnetic field, but whereas in the center it is opposing. But if you, as you proceed to the periphery of this magnetic field, or the flux lines at the periphery are actually happening to be aligning with the external magnetic field. Consequently, the protons, wherever they, for example, these protons which are attached to the aromatic ring, they feel the larger magnetic field compared to the protons which are happening elsewhere in the molecule. So these protons, or particular set of protons which are happening to experience the higher magnetic field because they are happening near this periphery, or near these flux lines, because the magnetic field here is aligning the external magnetic field. Since they are happening to be on the periphery, these protons experience a larger magnetic field when compared to the protons elsewhere in the molecule, and the aromatic ring protons therefore will resonate at the higher frequencies, and they further appear at the further downfield region, which is 7 to 8 ppm. So that is why the magnetic anisotropic effects, though they are sp2 hybridized carbon protons, I mean the protons attached to sp2 hybridized carbon, they don't appear at the shielded region, rather they appear at the deshielded region, or the downfield region, which happens to be 7 to 8 delta ppm, and this is what we call it as magnetic anisotropy. So the ring current, which generates a local magnetic field that opposes the applied magnetic field, However, on the periphery of the ring, the flux lines are in the direction of the applied magnetic field. This is what I am referring to. So the protons falling or the protons that are attached to this aromatic ring and happening around the periphery of this flux lines, they experience the larger magnetic field when compared to any other protons elsewhere happening in this particular molecule. That's the reason why this particular set of protons happen to be existing at the further downfield region. Similarly, coming to the acetylenic hydrogens, or which are the sp or the hydrogens which are attached to the sp hybridized carbon, the p electrons in the triple bond circulate around the bond axis to produce a magnetic field opposing to the applied magnetic field. The acetylenic hydrogen is shielded by the induced magnetic field and therefore will resonate at the p values. Okay, so these particular hydrogens, as you can see, they are not happening on the periphery of the flux lines, rather they are happening exactly in the center of this particular flux lines. So as they are happening in the center of this flux magnetic flux lines, they usually oppose, or they are experiencing the higher opposition to the external magnetic field. That's the reason they happen to be on the extreme right of the NMR spectrum, or they happen to be at a very shielded region or the upfield in the NMR spectrum, where usually the delta value is 2 to 3 ppm. The reason for appearance of this or the reason for the variation in their appearance is the magnetic anisotropy effect. So I would like to take up one next slide which has certain images where I would like to read out this first line before I go for the next point. The shielding and deshielding regions, due to various p electron functional groups, have characteristic shapes and directions. The shielding and deshielding region where we study in this NMR spectrum, or where the sp2 or the sp hybridized protons, where they appear, the shielding and deshielding regions, due to various p electron functional groups, have characteristic shapes. If you see, there are characteristic shapes over here. You can see the cones over this aromatic ring. You can see the cones over these double bonds, and you can see the cones across these triple bonds. So this figure, particular figure, illustrates this. There are number of different groups or different hybridized carbons, and the protons that are falling within the conical areas, or for example, if the proton is happening in this particular conical area, are very much shielded. That's why I have written, I mean, they are represented as a plus symbol here. And the protons, if they are happening outside this conical region, they are highly deshielded, since they are happening around out of this conical areas. Okay, so generally, if the proton is happening to be in the this particular conical areas, they are highly shielded. If they are happening outside this conical area, they are highly deshielded. So this is what we should remember, and this is how the magnetic anisotropy effects has a role to play, in particular with the aldehyde hydrogens. You can see, if you think this is an aldehyde, the proton happening here will be outside the conical, that is which is represented here, the conical shape or the conical area. If the hydrogen is happening outside this conical area, it happens to be appearing at a highly deshielded region, which is 7 to 8 or sometimes 8 to 9 delta values, which happens to be in the aldehyde. Similarly, in the benzene, if you see, the protons that are happening outside this conical area are highly deshielded. That's why the aromatic protons, they happen to be around at 7 to 8 delta values, whereas these protons which are attached to this carbon, which is sp hybridized carbon, which is having triple bond, the protons are happening in the conical region. That's why they are highly shielded. That's why they appear at the lower delta values, which is 0 to or 2 to 3 ppm. Yeah, 2 to 3 ppm. So this was about the magnetic anisotropy, and we should be very careful about the magnetic anisotropy, which is happening in the molecule because of the presence of pi electrons, and we should actually remember these areas wherein which these protons appear whether they appear in the downfield region, whether they appear in the upfield region, or the shielded region, or the deshielded region. Okay, thank you very much for listening to my videos.